This is the Chem 1 lecture for reaction mechanisms. So when we look at reactions, we see a set of reactants turning into a set of products. You see the very beginning and you see the very end. But all throughout that process, there's a lot of things going on. There's a lot of smaller individual steps that we don't really see. We call all these little miniature steps, we call them all together a reaction mechanism. So in chemistry, a reaction mechanism is the step-by-step sequence of smaller steps in which kind of come together to make an overall chemical reaction. The mechanism is very, very detailed, and it tells you exactly what happens and when it happens within a chemical reaction. So all these little steps that we see, we call elementary steps. And when you combine them all, you get to see the overall effect, your net reactants making your net products. We call that the overall reaction. You are used to seeing the overall reaction, what happens at the very, very end when you've kind of looked at all of your steps, you've canceled out what you can cancel out. You're used to seeing the beginning reactants making your final products. So here what we would say is a reaction mechanism. You would have 3 steps, step 1, step 2, step 3, and when you combine them all, you end up with an overall reaction. There's going to be more than a few new vocabulary words that we're going to talk about today. So the first one we're going to see is intermediates. Intermediates are things that are temporarily formed from all of these little steps. Essentially, an intermediate is something that is made in one step and then used in a later step. You don't see it as a final product because you use it and then you turn around and make it. That order is actually really, really important. It is first made, so it's first produced, and then in a later step, it gets used as a reactant. So it's both a reactant and a product, depending on the step that you're looking at. It doesn't have to be the direct next step, so here we only have 2 steps. But if there was a step 3, hypothetically, then we could, instead of using it directly in step 2, like we've done here, we could have used it later in step 3, and it still would be considered an intermediate. So as long as it gets made first and then used, we call that chemical an intermediate. So here's a potential energy diagram that actually shows every individual step. So the first question says, what letter represents the energy of the reactants? Well, the reactants are still the stuff that I start with. That's going to be A. What letter represents the energy of the final products? Well, that's still going to be the stuff at the end. That's going to be D. But then we ask the question, how many steps do I have in this reaction? Well, each one of these hills represents a step. So here's 1 step, 2 steps, 3 steps, 1 for each hill. Then it asks us to label the activated complexes. Back when we first started Unit 15, we learned about what activated complexes are, where they are on our potential energy diagrams. They're at the very, very top of the hill. So because we have 3 steps, we also have 3 activated complexes. 1 there, 1 there, and 1 there. 1 for each one of our steps. This is to label all the intermediates. Well, the intermediates are going to be things that are created and then used. So while this is kind of a weird question, what it's really wanting you to think about is the fact that your intermediates are going to be created and used here in step B and step C. They're going to be made in step B and then turned around and used in that next, either that direct next step, this next hill here, or turned around and used here. So you could have intermediates at B, or you could have intermediates at C. Last but not least, the last question says, is the reaction endothermic or exothermic? Well, overall, I'm losing energy from reactants to final products, so we would say that this is an exothermic reaction. The next little vocabulary thing that we need to talk about is something called the rate determining step. And we call the rate determining step the rate determining step because it is the one that essentially determines how quickly or slowly your reaction occurs. It is the slowest step in your reaction. Everyone's kind of heard the old saying, you're only as fast as your slowest runner. So if you're running a relay race, your final time is going to be heavily dependent on whoever is your slowest runner. Well, that's kind of how this works. In a reaction that has multiple steps, the step that is going to determine the rate that that reaction processes is going to be the slowest of the steps. So if you want another real world example, if you were wanting to walk from the school to the food court over at the mall, but you could break that into two little journeys, two different pieces. First, you walk to the mall, and then going up the escalator, because our mall, the food court at the mall is on the second floor. It's going to take a lot more energy just to walk to the mall, because once you get there, you jump on the escalator and you're basically there. So it's the rate determining step for walking to the mall food court to get food is going to be, do you have the time and energy to walk all the way to the mall? That would be your rate determining step, because it takes the most amount of time, aka it's the slowest, and it has the highest activation energy. Which brings us to writing rate laws. Rate laws are chemical formulas that help us determine the speed of a reaction. They are determined from the slowest step in your mechanism, your rate determining step. And all rate laws look really, really similar. The rate of a reaction is equal to K, which is a constant that comes from surface area and temperature, and it's dependent on a lot of different factors that we're really not going to go into, times the concentration of your reactant in your slow step to a power that we're going to talk about, times the next reactant in your rate determining step raised to a second exponent that, again, we're going to talk about here in a second. Remember these brackets here and here. If it'll write, that'd be helpful. There you go. Here and here represent concentrations, so molarity. And the exponents, those x's and y's, come about from the coefficients. So if I have so if I wanted to look at this example, I'm going to look at the slow step to determine my rate law, so I don't care about this thing right here. I'm only going to look at step 1, and the rate is going to be equal to rate equals K, a mystery constant you don't really have to worry about. And if I look, there's only one reactant. It's the same thing. If we say that that molecule is NO2, my bad. There's your reactant, NO2, and it would have a coefficient of 2 because there's 2 of them, so it would be raised to the second power. If that was a little confusing, don't worry, we're going to do more than a few examples of having you write rate laws here in just a second. And here's that example. So below is a proposed mechanism for a reaction. Find the overall reaction and identify the intermediates, and then we're going to write the rate law. So if I wanted to let's start by looking at what are intermediates. Remember, the definition of an intermediate is something that is first made and then used in a later step. So if I wanted to look at this reaction mechanism, well, here's step 1. I'm going to take HBr plus O2, and it's going to make HOOBr. Well, if I look at step 2, I turn around and now use HOOBr. So that tells us that HOOBr is an intermediate. Well, if I look at step 2, I now make HOBr, and I turn around and use HOBr. So not only is HOOBr, I also know that HOBr is an intermediate. I don't make anything else that I could turn around and use because, well, here's step 1, and there's step 2. So what I can do is to figure out the overall reaction, is I can cancel out my intermediates because I know I'm going to turn around and use them. So they're not going to be there at the end. So my overall reaction is everything that I'm going to start with, which is 1, 2, 3, 4 HBRs, because I have a total of 4, plus, and actually maybe I'll write it like this. I might make it a little bit clearer. So at first, if I look at step 1, I have HBr plus an O2. From step 2, I still have another HBr left. And in step 3, I then turn around and use 2 HBRs. I'm going to give us a little bit of room to write. Plus 2 HBRs. So you see we have all of our reactants there. An HBr plus O2 plus another HBr plus another 2 HBRs. And I can reduce that because I have 1, 2, 3, 4 HBRs. So that I don't have to write HBr 4 times. I can just write 4 HBr. So I have 4 HBr plus O2 well, I've crossed out that product because I used it in step 2. I crossed out that product because I used it in step 3, and I'm left with 2H2O plus 2Br2. And that becomes my overall reaction. Essentially, it's everything that's left after you've crossed out the intermediates. Last but not least, we can write a rate law. So when we write our rate laws, just kind of clear this off so we can start fresh. When we write our rate laws, we are only concerned with the rate determining step of our reaction, which means these 2 steps that are my fast steps, we don't care about them. They don't help us write the rate law. We only focus on the slow step. There's always only going to be one. So we know that a rate law is equal to the rate of K. Again, you don't need to know what K is. It's going to be different for every reaction at different temperatures. There's a lot of things that you don't have to worry about there. Times the concentration of my first reactant, HBr, to the power of its coefficient. Well, it has an imaginary coefficient of 1, so it's going to be raised to the 1 power, times the coefficient of my second reactant, so oxygen, raised to the power of its coefficient, which is 1. So our rate law for this reaction will be the rate is equal to K, a constant, times the concentration of HBr to the 1 power, times the concentration of O2 to the 1 power. All right, the last thing we're going to talk about are catalysts. We learned about catalysts a little bit in, the opening video for Unit 15. Catalysts are really, really similar to intermediates with a very important difference, one very important difference. An intermediate is something that you make and then use. So in this example, we make Fe plus 2, and then we use Fe plus 2. So these guys, Fe plus 2, would be intermediates. A catalyst is something you start with, you use it, and then you remake it later. At any point later, as long as you remake it, you're good. So if we looked at this example, Fe plus 3 is going to be my catalyst because I use it, it disappears, and then I remake it. In other words, an intermediate is a product, then a reactant later, whereas a catalyst is a reactant and then a product later. So they're really, really similar in the sense that both of them would cancel each other out. Neither of them would show up in your overall reaction, but the order they happen in is actually really important. Intermediates are first a product, then a reactant. They're made and then used, whereas a catalyst is something that is used and then made. In other words, a reactant and then a product. If you're still a little confused about rate laws or reaction mechanisms, that's totally understandable. Remember that you can always come in, try some more of the practice homework that we have provided, come ask us, come show it to us, and we'll be happy to go through any of it with you.